Now next we will come to the polar character of covalent bond. Polar. You have heard it many times, this word polar. Even I have also used previously, that is polar. Polar means what? Just now I said when two poles are there. But for that particular purpose, the two atoms should be of different electronegativity. That means it should not be between two similar atoms. It should be between two dissimilar atoms. Like just now I was saying, fluorine F2, that was a non-polar molecules because there is a bond between F and F. So both the atom have got similar electronegativity. One fluorine atom, another fluorine atom will have the same electronegativity. Definitely, they will have the same electronegativity. So if you find the difference in electronegativity, it will be 0, we can say that. Definitely, if you find the difference in electronegativity, one fluorine atom, whatever the electronegativity is there, generally it is 4. Alright, it is the same as the other fluorine atom, the difference will be 0. So hence it is said to be non-polar in nature, we can say that. Alright, for that reason we say it is non-polar in nature. But when there is some difference in electronegativity exists, alright, for example in case of HF molecule, it is polar because your fluorine is more electronegative and hydrogen is electropositive compared to that. They don't have the same value of electronegativity. They don't have, we know that. For example, HCl. Alright, for example, water. Alright, between hydrogen and oxygen, we can say that. That is water. Clear? So in this way, when there exists a difference in electronegativity, and difference in electronegativity will exist, or a difference in charges will exist. If you don't understand electronegativity, I can say use a simple word, charges will exist when you use two different atoms. So when two different atoms are there, then only the polar molecule results. Then only the polarity results, I should say that. So polarity develops, the polar molecule develops when there are two different atoms, we can say that. Then only the charges are unequally distributed because the oxygen is more electronegative than hydrogen. So oxygen is going to pull the electrons towards itself from the hydrogen atom. Got it? Here fluorine is more electronegative than hydrogen. What does it mean? Fluorine is going to pull the electrons towards itself from the hydrogen atom, due to which it gets slightly electronegative and due to deficiency it gets slightly electropositive. Alright, and hence the net result is that it is polar. As you can see, two poles are existing. Alright. So in this way, polar character or the polarity develops when there are two different atoms. Because if two different atoms will be there, then the charges are unequally distributed. Alright, for example, suppose I have got 10 chocolates. If I distribute equally between the two friends, 5 and 5, so it is non-polar. Because charges, I have distributed the chocolate equally, I have distributed the charges equally. But suppose to one I give 7, another I give 3. Alright, so what you will find is that the charges are unequally distributed. The chocolate is unequally distributed, 7 and 3. So 7 means excess. Alright, 3 means deficiency, definitely. So hence, when there is a difference is there created between them, then what is that? Polarity results. Alright, charges develops. So when polarity results, charges develops, then that particular substance or that particular compound is known as polar covalent compound. First of all, the compound has to be covalent in nature. Alright, so here definitely all these are covalent compound. Alright, clear? Because ionic compound, already the ions are present. No need to talk about it. No need to talk about it. Ionic compound, already the ions are being there. Already it is made up of cations and anions. Because we are saying already ionic compound. But covalent compound, the ions are not present. It ionizes. For that reason we use the word ionization in case of covalent compound, and we use the word dissociation in case of ionic compound. Listen carefully. Ionic compound dissociates because already the ions are present, just it gets separated. But in covalent compound, ions are not present, ions are developed. So hence we say covalent compound undergoes ionization, and we say ionic compound undergoes dissociation. These are the two different terms used for two different compounds. Alright, you cannot use it as you like, as you wish. Alright, so polar character develops when there is difference in the charges, when there is difference in electronegativity. Alright, so now in this way, greater is the electronegative difference, greater is the polarity. We can say that. Clear? Fine. Now how will you measure it? Actually, see, electronegativity is what? It's a tendency. So it is very difficult to measure it. Just different scientists, they have given different scale, like Pauling has given a scale, Hannes and Smith has given a scale, Mulliken has given a scale. So we have got a scale, understood? We have got a scale. We can't measure it, no? Like ionization potential, electron affinity, or which is called as electron gain enthalpy. It can be measured. We have got a value for it. We have got a unit for it. But electronegativity, we don't have a unit, you know that. Alright, it's a tendency of an atom to attract the shared pair of electrons towards itself. How to measure the tendency? So hence scientists have developed a scale. On the long research, they have got a scale. So one scale which is quite convincing to calculate the percentage of ionic character when the covalent molecule develops ionic character or polar character it develops, then how much ionic character is being present? Alright, how much ionic character is being present when a covalent molecule develops a polar character, ionic character? How much is being present? What is the percentage of ionic character? That we can calculate it. Alright, so we are having a scale from what you can say Hannay and Smith, H-A-N-N-E-Y, Hannay and Smith, we can say that. That is, but the spelling is of Smith is S-Y-M-T-H, not S-M-I-T-H, S-Y-M-T-H, Smith. Alright, it is spelled in different manner. So, in this way, Hannay and Smith has given a particular formula to calculate the percentage of ionic character. Alright, what I said? Percentage of ionic character. So, if I am able to calculate the percentage of ionic character of the compound, total percent is always 100. Let us say ionic character is 60% and 40% is covalent. Simple. Alright, 100 minus 60. So, how to do that? It is nothing but, that is, we can say, 0.16 into, this is called chi, you know that, chi A minus chi B, chi A minus chi B, 0.16 into chi A minus chi B plus 0.035 into chi A minus chi B whole square, whole into where should I write? 100%, because I need to convert into percent. So 0.16 chi A minus chi B plus 0.035 chi A minus chi B whole square, where chi A is the electronegativity of an atom, let us say hydrogen, and chi B is the electronegativity in another atom, which is, let us say, it is nothing but is your fluorine, let us say that. Alright, so in this way we are having the chi A and chi B, we calculate in this particular way, chi A minus chi B. Generally, we consider here chi A is more electronegative than chi B. Alright, so if I said H and F, then it should be F and it should be H, mind it. Alright, clear? So, in this way. So, generally we consider that chi A in chi B, that chi A is more electronegative than chi B, generally we consider that. Clear? Fine. In this way, we can calculate from Hannay-Smith observation, from scale, we can calculate the percentage of ionic character, we can say that. Clear? Now, next. After that, we'll come to, that is your nothing but dipole moment, we can say that. Clear? After this polar and non-polar. In case of non-polar molecule, already you know that percentage of covalent character will be 100% and ionic character will be 0. Covalent character will be 100% because chi and chi B both are same, we can say that. Clear? Because two atoms are similar. Alright, two atoms are similar, like chlorine, like nitrogen, oxygen, they are said to be as what you can say non-polar molecules. Some non-polar molecules are more are there, heteroatomic non-polar molecules, we'll come to it now. So, dipole moment. What is dipole moment? Dipole moment is a molecule is a product of the net positive and the negative charge and the distance between them. What I said? Dipole moment of a molecule, you can write it down. Dipole moment of a molecule is the product of net positive and negative charges and the distance between them. Alright? Is a product of net positive and negative charges and the distance between them. So, dipole moment is noted letter mu. Mu is equal to, what you can say, E into D. E is nothing but the net positive and the negative charge. What do you mean by net positive and negative charge? For example, let us say an HF molecule, I am taking it. So, HF is positive and fluorine is negative. What will I do? I will subtract the electronegativity. Just now I am saying that you will subtract the electronegativity. That is called the net positive and negative charge, which is known as E. Now, while subtracting the electronegativity, the value, when I will subtract the value of the electronegativity, which is being given, it will be given to you, don't worry, it will be given, nothing to learn, you cannot remember it. It will be given. So when you will subtract the difference in electronegativity, you may get the answer to be as positive or you may get the answer to be as negative. That is called as E. Net positive or negative charge. Net means a difference. You may get this answer to be positive, you may get this answer to be negative. Definitely. Because on subtraction of two electronegativities, the answer may be positive or may be negative, whatever it is. So that value will put it here. And D is the distance between them, means bond length. That is called as a bond length. D is the distance between them. Alright. So generally we represent the dipole moment in this particular way. We represent it in this way. We draw an arrow and we cut the tail of the arrow. The tail, when we cut it, it represents what? You can see plus sign. So it's always represented from positive to negative. The arrow is always directed from positive to negative. Alright, for how positive? You just show an arrow from positive to negative and you cut the tail of the arrow. That's it. It becomes positive in this way. We represent a dipole moment, and as it has got a direction, dipole moment is a vector quantity. It is not a scalar quantity, it is a vector quantity. It has got direction. As you can see this, it has got some direction. Fine. Now, you understood what is dipole moment? It's the product of net positive and negative charge and the distance between them, I said it. Now, what is the unit of dipole moment? I already said the dipole moment is measured by unit that is called as debye. D-E-B-Y-E, denoted the letter capital D. We can say that, debye, we can say. Alright, but we have got some other CGS and SI system also. In CGS, we have got ESU centimeter. Because you know in CGS system, the charge is measured in electrostatic unit. Charge is measured in electrostatic unit. So this is charge, the net positive and negative charge. ESU, what I said? Centimeter. ESU centimeter. This is the unit for in the CGS system. In SI system, the charge is measured in coulomb and this is what? Meter. That is coulomb meter. You can say that. Now, generally, what you find is that the D is in the order of D, the distance between them is the order of 10 to the power minus 8 centimeter. You know that. We take it as. There is the order of 10 to the power minus 8 centimeter. The distance between the two charges. It cannot be still lesser than that. It's not possible. 10 to the power minus 8 centimeter. And the charges which you are having it, that is the net positive and the negative charges which you are having it, it is in the order of 10 to the power minus 10 ESU. Generally, in most of the cases, it is 10 to the power minus 10 ESU, and this is 10 to the power minus 10. This is ESU. I hope you can see it. ESU. Alright, and 10 to the power minus 8 centimeters. So, how much you get it? 10 to the power minus 18. 18 ESU centimeter. We can say that. 10 to the power minus 18 ESU centimeter. Alright, in this way generally it is being done. Generally, this is on an average for an atom I am saying you. Generally it is being done. It's done. And the value of 1 debye is 3. In CGS, in SI system, this is in CGS system, in SI system 3.336, it is being calculated. 3.336 in 10 to the power minus 30 coulomb meter. Alright. That is 10 to the power minus 30 coulomb meter. That is 1 debye is 3.336 and 10 to the power minus 30 coulomb meter, because we convert this ESU to coulomb and centimeter to meter. We convert it and hence we get this particular value. That is 1 debye and after that we convert it into debye, and 1 debye this much coulomb meter, we can say that. You may require it while doing the numericals, you may require it. Alright, so in this way you understood how we are representing a dipole moment. We are representing in this particular way, manner, we can say that. So dipole moment for a diatomic molecule, I said you this. This is for a diatomic, 2 atoms. For a diatomic molecule. Now what about the dipole moment for a triatomic molecule? For a triatomic molecule, we can say that dipole moment. Now triatomic means, for example, let us take a water molecule. Water. 3 atoms are there, H2O, 3 atoms. So in case of triatomic molecule, we find it out in this way. This is a resultant dipole moment, we can say that. This is the resultant value. Got it? Now let us say this is your A and this is B, we can say that, and this is also another B, we can say that. Let us say water. Water means this oxygen, this is 2 or hydrogen, and this is the net dipole moment, the resultant dipole moment is this. Alright, so this is nothing but is your mu AB, and this is also is your mu AB. Mu is the dipole moment, you know that. Alright, now if it is making an angle theta, then this angle is nothing but theta by 2, and this is your resultant dipole moment, which is mu. Now how will you calculate mu? You have studied in vectors, you have studied in physics vectors. that is triangle law of vectors. Mu is equal to root over of mu1 square plus mu2 square plus mu1 mu2, what is that? Cos theta. Alright, that is mu1 square plus mu2 square, sorry, 2 I am missing here, 2 mu1 mu2 cos theta. That is a square plus b square plus 2ab cos theta. We can say that. Clear? That is said to be as root over of the resultant dipole moment. For example, suppose what is the resultant dipole moment of water? Actually, resultant dipole moment of water is 1.84 dBi. For water, we can say that it is 1.84 dBi. It has got a very high dipole moment. We can say that. So how do we measure it? For triatomic molecule, we use this particular formula. You have read in physics this particular one. This one is triangle law of vectors. We can say that. Clear? We have studied this formula in physics because it's a vector quantity, so to say. But that does not mean that all triatomic molecule will be measuring in this way. No. For example, in case of carbon dioxide, CO2, it is linear. Alright? Because dipole moment from this to this and from this to this is same. So you know, if two vectors are there in opposite direction, the resultant vector is what? 0. If two equal and opposite vectors, see this particular vectors, the dipole moment is 2.3 dBi. This is also 2.3 dBi. So 2.3 net dipole moment is what? 2.3 dBi minus 2.3 dBi. Mu is equal to what? 0. For that reason, carbon dioxide is linear in nature. So from the dipole moment, what we come to know about the shape of the molecule. If a molecule has got a particular shape, then it will be non-linear. Remember, if a molecule has got a particular shape, it is non-linear, and it has got also certain value of dipole moment. Water, it is non-linear. What is shape of water molecule? Even if it is triatomic, it is what? V-shape, bend shape. We can say that bond angle is 104.5 degree. We have already studied. Now this is also a triatomic molecule. But why the shape is not the same as water? Because here the resultant dipole moment cancels the effect of each other. Here the resultant dipole moment does not cancel. Here it is from hydrogen to oxygen. Isn't it? Hydrogen to oxygen. And the resultant dipole moment is upward in this way. This is your resultant dipole moment, which is upward. Clear? 1.84 dBi. This is for water. It is upward. The resultant dipole moment is. Because you know hydrogen is here positive and oxygen is here negative. So in this way, you can find it has got certain value of dipole moment. It has got some resultant. It has got certain value, which is 1.84 dBi, as you can see it here. In case of water, but in case of carbon dioxide, it is not so. It is cancelled here because the two vectors are equal and opposite. So the net vector is 0. The resultant vector is 0. So hence it is linear. So basically, the molecules which are linear in nature, they have got 0 dipole moment, and which are non-linear in nature, they have got certain value of dipole moment. And they have got a particular shape. Non-linear I said, they have got a definite shape. We can say that. Clear? Fine. In this way. This is about your dipole moment, so to say. Some more are there. We'll see it. Thank you.